Hey guys, Bert Kammerer here, and today we're going to follow up on our previous episode where we taught you how to create a very basic model using HTX on the Radiomaster TX16S. And today we're going to get into RotorFlight. We're going to create a very basic model using RotorFlight and the Nexus Flabberless system with the RP3H receiver. So the first thing we're going to do here is we're going to go ahead and get our Nexus Flabberless unit ready. We're also going to need the RP3H receiver to be handy. Although we don't need the receiver at this very moment, we do need the Nexus. So first thing we're doing is we're going to go to a website and download RotorFlight Configurator. So we're going to go to rotorflight.org. And when we get to that website, we're going to click on download right here. And that's going to take us to the downloading section for the configurator. We're going to click on download the current release. And as of right now, it's version 2.1. But these change very, very quickly. So for all intents and purposes, the relevancy is the same. It doesn't matter what version it is. Just click on that. And then it'll take you to the download page. If you scroll all the way down, you're going to find under assets the different installer files for different systems, right? So if you have Windows 32 or 64 or AMD, or if you have Linux or Mac, I do have Mac, so I'm going to go ahead and click on Mac OS .dmg, and that's going to download the file to my computer. Once I am done downloading the file, I'm going to go ahead and fire up the actual configurator, and my screen will look like this. Now I'm in RotorFlight Configurator, and I'm going to go ahead and get my Nexus right here, and I'm going to go ahead and plug it in. So you should have a USB-A to USB-C cable that comes with this device. The cable I have right here is slightly different, but it serves the same purpose. I have USB-C to USB-C, but at the end of the day, it doesn't really matter. When you connect your USB-C to USB on your computer, if everything is correct, your computer is automatically going to connect to your Nexus with the configurator, and you're going to know you're connected because you're going to see the helicopter here. It says info configured, this and that. So what we're going to do first is we're going to go ahead and disconnect, okay? And the reason we want to disconnect is because we want to update the firmware on this unit, and this is something I highly recommend everybody to do. First, before you do anything, go ahead and update the firmware on your system, and whether it is the Nexus or the FlyDragon, this is something you have got to do. So click on update firmware, and then you can leave this as releases and pre-releases up here, and then here you can choose the board you have. So you can either search for the Nexus, or you can just click on detect, and it should detect it right here. And as you can see, Nexus _F7 has been detected. That is correct. And then these are the releases that are available. I was running 4.4.0 RC1, which was released on November 1st, right? But now, as of January the 9th, they have 4.4.0, and it's no longer an RC123, meaning it's not a release candidate. It is a stable version. So we're going to go with that stable version, latest and greatest. Now these options right here don't really matter much, but the full chip erase is something I always check. And this is because if you're updating and flashing firmware from a unit that had older software to a much newer firmware or software revision, you kind of want to erase the entire software on the flight controller itself. So it does not hurt to do that, especially if you know what you're doing and how you're going to do the next setup. If this is a brand new unit, it doesn't hurt to just do a full chip erase. Just go ahead and check that. And then scroll all the way down and hit load firmware. And you're going to see that it loaded it. And then you're going to click on flash firmware. And the first thing it's going to do is it's going to erase the chip, which it's doing right now. And then after it does that, it's going to start flashing. Now, again, this is something that is super important that you do. Whether you have the Nexus or the FlyDragon, it is always recommended that you use the latest and greatest version, especially if it's a stable version. So we'll wait here for this thing to be done flashing. And then after it's done flashing, we should be able to connect. If you have any connectivity problems, it has to do with the port your computer wants to naturally use. So programming successful. So I'm just going to click on connect up here. And as you can see, I'm connected. And I can tell I'm connected because I can see here status info configured. And if it's a brand new unit, or if you erased the information in the unit, you're going to see this warning. There's a problem with your configuration, which is the accelerometer is enabled but is not calibrated. So the first thing you do is you calibrate the accelerometer. So I'm going to close this message. I'm going to show you how to do that. The key to calibrate the accelerometer is basically for the unit to be sitting on a flat surface. I know my desk here is as level as it can be, so I just leave my unit sitting like that, and I go back to RotorFlight Configurator, and I click on Setup right here on the left, and then I click on Calibrate Accelerometer, and it takes about 2 to 3 seconds, and it's done. Now I'm calibrated. So if I go here and disconnect, and then I reconnect, you'll see I don't get that warning that I'm not calibrated. So everything should be fine at this point in time. So the next thing we're going to do is we're going to go ahead and mount the Nexus flybirless system to our helicopter. Let's take a look and see how we do these connections right here. First thing we're going to do is figure out where each servo gets connected to. So the first port is S1, meaning servo 1, and then servo 2 and servo 3. These are your 3 cyclic servos. And the way they get connected is servo 1 is always going to be your elevator servo. So if your elevator servo is in the rear of the helicopter, that will be servo 1. And then you're going to follow the servos in a clockwise direction as viewed from the top. So if your elevator servo, for example, is in the back of the helicopter, then S2, servo 2, will be the one that's on the left, as we would say in boating terms, the port side. And servo 3 will be on the right, the starboard side. So again, follow a clockwise orientation or a direction to where elevator and then the other 2 go in clockwise motion, so 1, 2, and 3. The next port will be your tail servo port. And the next port will be your ESC port, which is obviously where you connect your ESC main lead. And then you have the RPM port, which in Hobbywing would be the actual RPM lead that comes out of the ESC. And then you have one more here, S-Bus, and that could be open. Obviously, if you have a Futaba radio, you would hook it up to S-Bus. We're dealing here with a Radiomaster TX16S running Express LRS, so that port will be open. So you could use this for telemetry from your Hobbywing ESC, or you can also use this DSM port for telemetry. So what we're going to do is we're going to go ahead and take our RP3H receiver and we're going to plug it into port A, just like that. And then we're going to go back to RotorFlight Configurator. We're going to plug this in. I want to show you something before I mount this on the helicopter. So I'm going to plug it in and I'm going to go back to RotorFlight Configurator right here. As you move the Nexus, the helicopter moves, right? The Nexus is set up in a way to where the servo leads, as shown right here, are supposed to be forward. The side that has the USB-C connector should be in the back side of the helicopter. That's what it's pre-configured for. And as you can see, if you picture the nose of the helicopter being that way, as I go forward, the helicopter goes forward. And as I go back, the helicopter goes back. And then right, and then left. Now, I never mount a flybirless unit with the servo connectors facing forward because it's a lot more cumbersome and difficult for me to make changes or to unplug a servo or replace a servo or inspect my connections. I always mount it with the servo leads facing the back of the helicopter. So I'm going to show you how to make that quick change right here. So you go on Rotor Flight Configurator. All you have to do right here is go to the configuration section, and down under board and sensor alignment, if you're going to rotate the unit from this being forward to this being forward, you're rotating the unit 180 degrees in the yaw axis. So what you do is you go in here, and where it says yaw degrees, you're going to do 180. And then you have to basically, to make that change, you have to save and reboot. And it'll reboot and it'll reconnect. And then once it reconnects, then you can see how this has changed to where now if the nose of the helicopter is that way, when I tilt forward, you see the helicopter goes forward. This is important. You got to make sure that everything is correcting in the right direction. So anyhow, a little detour right there, but what I'm going to do now is I'm going to go ahead and install the Nexus and the RP3H on my Tron Advance 7.0, and we'll move on with the setup. All right, so I have now my Nexus and my receiver installed on my Tron Advance 7.0. So I just plugged it in. So now I'm going back to Rotor Flight. So if you guys remember when we showed you how to create the model on your Radiomaster TX16S, we very, very briefly went over these settings right here. And I'm going to have to change these, as I can see right here, one more time, because the channel arrangement is a little off, and we're going to go over that one more time. We already clicked on setup and we calibrated the accelerometer before we put the Nexus on the helicopter, and it is important that you do this before you install your flight controller on the helicopter, because you can find a more guaranteed to be, I guess you could say, horizontal surface to do this with. When it's on the helicopter, it could be tilted, angled, or anything else. As you can see right here, it's very hard to tell, and I apologize for the poor lights, but I'll have it installed right there, and you know, it's hard to tell if it's level or not. You know, helicopters sometimes they tend to kind of lean forward as you're on the skids or whatever. So it's better to calibrate ahead of time before you proceed to mount it on the helicopter. Let's get back to Rotor Flight here. And so we're done with setup. And then the next thing is configuration. So you're going to give your helicopter a name. In this case, I choose to name my helicopter Tron Advance, and then you're going to go into the system configuration. There's not a whole lot that you have to do here. Basically, you can't change that, of course. You're going to go ahead and leave the PID loop frequency the same. It's not worth messing with it, to be honest. Leave the accelerometer and the barometer turned on. You don't need a magnetometer. The Nexus does not have that. And then you can leave these settings here alone. No need to mess with that. And then when you get to the serial ports, okay, so here where it says port A, as you can recall, we installed the RP3H receiver. So I'm going to change that to serial RX. And then I plugged in my Hobbywing telemetry cable into the DSM port. So I'm going to set that to ESC telemetry. And I'm going to leave these as auto and auto. All right, so we're going to go ahead and save these changes and reboot. And it connects right back in. So we're pretty much done here with the configuration section. Okay, so now that we're done with the configuration section, we're going to get into the receiver section. So let's take a look at this receiver section right here. First thing you got to do is you got to select the protocol. Since we're using ELRS, we're going to go to TBS CRSF, basically TBS Crossfire. And then when we get to the inverted serial signaling and all that kind of stuff, you can leave all that alone. You can leave this alone for now. We're going to get into that here in a little bit. And then under telemetry, I'm going to show you how to set this up later in a future episode. But for now, you can turn that on. And then you can turn all your sensors on right here. I prefer to use the CRSF custom telemetry. And again, I'm going to explain that in a future video. But for now, you can just turn telemetry on, turn all these settings on right here. Something that is very important that we talked about in a previous video is your channel assignment. You want to make sure this is set to AECR1T23. And what that does is that changes the channel arrangement or assignments to roll pitch. So basically aileron elevator, collective, rudder, aux1, throttle, aux2, aux3. And the reason why you want that is, as we discussed before, you want the first 4 channels to be aileron elevator, collective, and yaw, because those are your fastest, highest resolution channels provided by Express LRS at higher rates of transmission. So throttle is not as important, of course, in terms of the resolution that you're going to get out of it. So you want those primary 4 channels there. And that's how I taught you earlier how to set up your model with the TX16. So this will work very, very well with the way that you have your transmitter set up. Once you're done with that, you're going to go ahead and save and reboot. And then what we're going to do is we're going to turn on our transmitter, and we're going to look to see what the PWM signal in microseconds is for the throttle, so we can adjust that. So what we're going to do right here is I have my transmitter. I already powered on, and remember, you don't have to plug in your receiver pack or your fly pack in order for RotorFlight to show you movement. If I move the sticks here, you can see them moving. So your servos are not going to move, obviously, but it doesn't really matter. So what we're trying to do here is we're trying to see where that throttle is. So right now I'm in throttle hold, and as you can see here, it's probably hard to tell on the screen, I'm at 988, and that's throttle hold. It's 988. Now, if I release the throttle hold, it's 2011. Now, that is with my safety switch on. Remember, the arming switch has nothing to do with the throttle setting, because the arming switch is only affecting right here, the aux1, which is what's the arm and disarm. And if you remember from a previous video, way down here, we haven't gotten there because this is a fresh install, but right down here, the arm was set right here in this screen. And I'm going to get to that one more time today as I do this video with you guys. But anyway, going back to receiver. So I wanted to check to see, so if the throttle is all the way down to 988, so what I'm going to do, and you know, everybody has a different opinion about this, and I'm good with, you know, I don't think this is so strict. But I'm going to leave under receiver settings the stick center at 1500, and then the maximum travel, I'm going to go to like 511 from 110. Why? Because when I move for example, aileron, you can see how it goes to 2011. So from 1500 to 2011 is 511. And so that's going to be my stick maximum travel. For the throttle channel limit for arming right here, I'm going all the way down to 990, because when I'm disarmed, my throttle is at 988. And then for my throttle channel value for 0%, I want 1100, because I want a little bit of buffer between arming and zero throttle, right? And then for throttle channel value for 100%, as you can see here, maximum throttle 100% is 2011. So I'm going to do 2010, which is perfect. And then this is probably a little different default. I already played with it a little bit, but the yaw deadband, I like to increase it to 3. Some people run it at 5. And then, as I explained before, telemetry for now, we're going to deal with that later. But once we're done with that, we're going to save and reboot. All right, so let's keep moving. So the next screen right here is going to be the fail-safe screen. You do not need to do anything here. These values work for almost everybody. Personally using these values, I know a lot of people are using these values. You can click the help button here if you want to learn more about fail-safe. But for me, these values are fine. Up next, we have the power screen. So as you can see, I already changed it. So what I basically did here is I changed this from the default to ESC telemetry for both the battery voltage source and the battery current source. I didn't mess with any of these numbers. I left the maximum cell voltage at 4.3, full cell voltage at 4.1, warning cell voltage at 3.5, minimum cell voltage at 3.3. I did enter 5500 for the capacity, because that's typically the capacity I'm going to be flying on this Tron Advance 7.0. So I enter that there, and then I saved and reboot. And then we get to the critical part here, which is the motors tab. Now, when we get to the motors tab, we definitely need to select an ESC telemetry protocol. I fly Hobbywing, so I'm going to select, and I have a brand new 260. That's a V5, so I'm selecting Hobbywing Platinum V5. You can pick whatever you have, Scorpion or anything else. The protocol, I missed that, but PWM is what works for most ESCs. If you have a special ESC that's capable of one-shot or multi-shot protocols, you can select that here, but I know that for Hobbywing, PWM is the way to go. And then I normally select these three options here. I have the one-wire communication, then I have the RX-TX pin swap selected and the RPM sensor selected. And then I leave these values alone. So the ESC update frequency is pretty low, 250 hertz. That's what Hobbywing likes. And then the motor stop at 1,000 microseconds, the 0% at 1,070, and 100% throttle at 2,000 microseconds. And these values are different than the ones we looked at before, but don't worry about it. That works really well. Up next, we have to deal with the gear ratio. This is super critical. So my Tron Advance is going to have a 16-tooth pinion. We're going to enter 16 here. So you put the pinion here and the main gear count here. The main gear count on that helicopter is 151. And as you can see, my main rotor gear ratio is 9.44 to 1. And then for the tail, the helicopter has a 22-tooth tail pulley, and it has a 127-tooth front tail pulley. So my tail gear ratio is 5.77 to 1. And then for the main pole count, my Xnova motor is a 10-pole motor. So selecting that. And then as we scroll down, the governor features. So this is where you have to choose whether you want to run the built-in governor that is part of the rotor flight control loop system. So you set it to standard. I like the internal governor to the Hobbywing. So basically external governor as we know it from the V-bar days. So basically the built-in Hobbywing governor. So I can set this to off and use the Hobbywing governor, but I like to set it to pass through. And the reason being is, we're going to get to that later, but this allows me to set the percentage of throttle I want the Hobbywing to see on my profile screen. So I go to pass through, and then what I do is I do something very similar to what Jonas does. I do the handover throttle at 20%, and then startup time is 20, and spool up time is 10 instead of 0. And then I'm going to set that, the spool up time to 0, because Hobbywing's going to handle that. And then my tracking time is 0. And then my recovery time is going to be also 0. And my auto rotation bailout time is going to be 0.1. And then the auto rotation bailout itself is going to be, let's do 30 seconds. So basically, if I go into auto rotation mode, I have 30 seconds to bail out. If not, it goes back to standard slow spool up. The next one is the minimum entry time, for auto rotation. I'm just going to change that to 0.1. The 0 throttle timeout, I'm going to leave alone. The head speed signal timeout, I'm going to leave it alone. And then the head speed filter cut, also alone. And then battery voltage filter cutoff, also leave alone. TTA bandwidth, I'm going to leave alone. And the pre-comp bandwidth, I'm going to leave alone. So that is my pass-through setting in order to use the Hobbywing governor. So then I'm going to hit save and reboot. So now I go back to the motors tab. And now what I'm going to do is I'm going to teach my ESC what the maximum throttle is and what the minimum throttle is. So in order to do this, what I'm going to do is I'm going to go ahead and plug in my helicopter. I'm going to plug it in. And the reason I'm doing that is I want to see this came alive. So my battery voltage is 45.4 volts. So it's a dead battery, which is fine. Please do not do this with your blades on the helicopter. Remove your main blades and your tail blades. And we're trying to see if RotorFlight can send the correct throttle signal to the ESC, and then we're going to calibrate the ESC. In order to do that, before we get there, I just enable the motor overwrite, and I start moving the slider to see if I get the heli to spool up. And there it goes. It does spool up. Okay, so that works. So what I'm going to do now is I'm going to go ahead and unplug my flight battery, and I'm going to go to wide open throttle, and I'm going to plug it in, and I'm going to wait for some beeps. And then I'm going to go to an idle. So here we go. There you go. Now it learned where the maximum throttle is and where the minimum throttle is. So now, theoretically speaking, we should be all calibrated on the ESC. So now if I move the slider a little bit, it should start to spool up after a certain percentage. And it should start to give me an RPM. And it'll give me that RPM right here. Okay, so at 70%. Whoa. At 70%, I'm at 2190. At 60%, I'm 1925. So what about, 60. At 80%, I'm at almost 2500. Now you might be wondering, why are the head speeds so stupidly high, ridiculous? This motor is way, way too high of a KV for this helicopter, but it's a lot of fun. So I know that with my V control, I was getting upwards of 2600 at 82%. I think the KV on that motor is about, it doesn't say because it was custom made for me, but it's probably like in the 560 range, which is insane. It's a 4530 560 or something like that. Okay, the next section we're gonna talk about is the servo section. So we're gonna go back to RotorFlight while connected to the machine, go to the servo section. Now this is very important. You have got to do this before you power on your transmitter. Remember, so far when we were messing with the motors and we hit throttle override, the only signal that was being sent through the Nexus inside the machine itself was going to the ESC. We have not sent the signal to the servos yet, because even though we plugged in the flight pack, we were controlling things through here. We didn't have the transmitter powered on. It's important that you do not power your transmitter until you get the servo configuration at least set to the right center pulse width. So this first value right here where it says center is your center pulse width for the servo. So it's commonly known as 1520 center pulse in microseconds, but it's really 1500. So you want to make sure that these are at 1500. Some people will argue that when they run 760, which in this case is 750, that they can increase the hertz rate to the servo. And yes, this is true. And some people argue that you have a lot better response, the helicopter feels better and crisper. Well, I'm, I guess, not that good of a pilot to notice the difference. Although I have run many helicopters with 760 center pulse width and a higher hertz, like 500. I normally like to set up on my first flight to set it all at 1520, because when the servo is running at very high rates of speed or hertz, if you have any kind of vibration, even if it's a tiny little high frequency vibration that is not visible to the naked eye, it can cause serious problems, and actually it could even cause a crash, or it could overheat the servo. It can definitely shorten the lifespan of the servo. So anyhow, most cyclic servos are pre-configured out of the box to run at 1520. So you got to make sure that this center value starts at 1500. Then over here, you're going to leave these values alone. The minimum minus 700, maximum plus 700, the scale negative and scale positive at 500. And then the hertz, on most servos, 333 is okay. If you want to be super safe, you can go down to 250. but 333 is highly recommended. Then as you move down here, this is why this becomes important before you power on your transmitter. My tilt servo is a Theta Razor T1, and I know that servo is a 760 center pulse width, so we're going to do 750 for that. And then because we made that change there, we're going to go ahead and cut all these values in half. So the minimum is negative 350 instead of negative 700. Positive is plus 350 instead of plus 700. And then the scale negative is 250 and the scale positive is 250. I also like to run a higher hertz rate for the tail. Usually the tail is okay with 500 hertz if your servo supports it. Remember, the hertz is not a function that you can program your servo with. It's something that your servo either accepts or does not accept. The center pulse width is something that you can program on some servos, but the hertz is basically what the servo can accept. You cannot change this on the servo. The servo has to be able to accept these hertz rates. I know Theta tilt servos can accept up to 1,000 hertz. Again, same scenario here. I don't want 1,000. I think it's too high. All it's going to do is going to overheat the servo over time and shorten its life cycle. And I really don't notice much of a difference between 500 and 1,000. So once we've done that, I'm also going to turn on geometry correction. This helps correct geometry issues that are induced naturally by the servo arc motion. So we're going to turn these on. Do not turn geometry correction on the tail because it's not needed and it's going to have some adverse effects. So once we've done this and we make sure that our center is correct, the right center pulse width and all these values are correct and the hertz is correct, geometry correction turned on, I'm going to save and reboot. Now I'm going to plug in my flight pack, right? And what I do for that is I normally unplug rotor flight first, because if you plug in your battery pack and you leave rotor flight plugged in with the USB-C, sometimes it does not really work. I'm going to plug in my battery pack right here. And then I'm going to plug in my USB-C into the Nexus, and now I'm going to go back to the servo section. So now I can enable the servo override, because now I'm going to be sending a signal straight to the servos, and I'm not worried that I have one of these settings set incorrectly. If I wouldn't have changed my tilt servo from 1500 to 750, it would be pegging itself to one side, and we don't want that. So the next step here is to make sure that the servos are moving in the right direction, right? So I'm going to change the screen here so you can see the helicopter and the servos. So if I click here, and it's hard to see because the picture-in-picture, but if I click here on the enable servo override, then I should have control over my servos. So as you move the sliders, and if you move them and you don't let go, it's nothing's going to happen. But as you move the sliders, the servos should be moving. And I'm looking for servo number 1, which is my elevator servo back here. And when I move the slider to the right, that servo should go up, and it does. So I'm good with the direction there. Now servo number 2, I don't know if you can see it on the camera, is moving opposite. So when I go up, servo moves down. When I go down, servo moves up. So I'm going to go ahead and reverse that servo number 2 right here. Yep. And then I'm going to check on servo number 3. And when I go to the right or up, it goes up. So that is correct. So, all right. So now our servo directions are right. Now you have to do the same thing with the tail. But we're not going to deal with the tail at this point in time because we don't know if we have to reverse it or not. It's not as easy to tell as it is with the cyclics, because the whole goal with the 3 cyclic servos is to make sure that when you move the sliders that they're all moving in the same direction. But with the tail, we really don't know in which direction it's going to move until we power on the transmitter. So we're going to deal with the tail later. Now, with that said, the next step here is to center the servos. So what we're trying to do with centering is we're going to be changing these values, this 1500 for each one of the cyclics and the 750 for the tail. And the easiest way to do that is to use your keyboard up and down arrows. And you start moving these values until you have perfect centering on your servos. And what I mean by perfect centering is I want to make sure that my cyclic servos are at a perfect 90-degree angle. I don't really look at the swash plate because the swash plate could be not leveled because the linkages that go from the servo horn to the swash plate might not be equal. I don't really care at this point in time about the swash. I just care about all 3 cyclic servos to be at a perfect 90-degree angle, geometrically correct. And I also want to see the tail servo to be at a perfect 90-degree angle from itself so that it has the same range of motion forward and back. So I'm going to go ahead and cut the video here. I'm going to look at all my servos and make sure these values are set to have a perfect 90-degree angle on my servos, and we'll be right back. So now all my servos are perfectly centered. Servo 1, 2, 3, which is cyclic, and servo 4, which is tail. And these are the numbers that I ended up with right here. And it's, you know, this one's within 2 microseconds of 1500. This is 21 off, and this is 29 off. It's perfectly acceptable. I know some of you like to center your servos first, especially if you have programmable servos. You program them, center them, and then these numbers would not change. I don't think Rotorflight cares if it's 20, 30 microseconds off. Once the system initializes and it boots up, it considers that the perfect center for the servo. Most servos nowadays have a lot of travel. We only use a fraction of what they're capable of. Now, what we're going to do is, before we move forward, the next step is to go into the mixer section. But before we go to the mixer section, I want to show you something that I like to do, just to make sure that everything that we've done thus far is working correctly. So we're going to take the transmitter and we're going to power it on. I might get the switch error because I forgot to turn my switches. And again, if you didn't watch the previous video where I talk about setting this up, I highly recommend you do. So I'm going to go to throttle hold and disarm, and now my transmitter is up and running. So what I'm going to do is I'm going to plug in the flight pack on my helicopter. I'm not connected to Rotorflight. I'm just going to plug in the flight pack. I know I'm in throttle hold and I'm disarmed. And you can see right here where the swash plate is going to initialize. There it goes. So what I'm trying to see is if the swash is moving in the right direction. And you can see it is. Now my cyclic might be off, and it right to left is good. Back and forth is backwards. That's what we're going to correct in the mixer screen. But I just want to make sure that things are connecting. My servos are centered. And then I'm going to check my tail movement. And you can't see it on camera, but the tail is moving backwards. So we're going to fix that. And I know that because on this Tron Advanced 7.0, when I move the stick to the right, the rudder, the pitch slider should be moving inwards in the helicopter to create a right tail input. And it's not, it's backwards. So we're going to fix the tail here in a minute. But before we do that, I'm going to go ahead and arm the helicopter and release the throttle hold. And it should spool up on me. And there it goes. So I know that works. So back to throttle hold. So I know all these things are working. So now what I'm going to do, I'm going to go ahead and plug the helicopter. And I'm going to go to the servo screen once again. And I'm going to reverse the servo number 4, which is my tail servo. And I'm going to save that setting. And now my tail servo is set up the right way. So we're basically good to go so far. So the next thing we need to do is we need to go into the mixer screen. Okay, so when we get to the mixer screen, before we do that, what we're going to do is go ahead and connect the helicopter. And I apologize for my clutter here in my working room. So I'm going to power on the transmitter. Then I'm going to plug in my helicopter. And once my helicopter is plugged in with the flight pack, I'm plugging in the USB-C. And so the first thing we want to look for right here when we go to the mixer screen is we want to make sure that these settings are correct. So of course, most helicopters nowadays are CCPM 120. the rotation is clockwise, unless you have a very massive, large scale helicopter that goes counterclockwise to mimic real life helicopters. And then the aileron control direction. So as you move the aileron on your transmitter, okay, so this is right, this is left. So that is correct. So our aileron is correct. Then the elevator right here, we're going to check elevators. So this is back, this is forward. So as you can see, it's backwards. When I go back, it goes forward. When I go forward, it goes back. So we're going to go ahead and change the elevator control direction to reverse. Save. And then now back should go back and forward should go forward. And that is correct. And then the next one is going to be collective. And the collective, as I showed you earlier, seems to be correct. Positive, negative. So that is all correct right there. So after we get to that, we're going to get into the main rotor geometry. Now, before that, there's a swash plate trim setting. So the roll trim and the pitch trim, what these do is they actually change your swash plate angle. So like if your swash is not perfectly level, which it should be, because as I explained before, if you set up your servos at 90 degrees during the servo trim section under the servo screen, and then if your 3 linkages from the servo horns to the swash are equal, your swash should be perfectly level. But if your swash is a little bit off, then you can go in here to the roll trim or the pitch trim, pitch meaning elevator, roll meaning aileron, and adjust this. Now, there's no reason why you should have to do this if your swash is level, and again, your swash plate should be level. With that said, the collective trim is a critical part of the whole thing. And if your blade grip angle is not 0 degrees, then this is something that you have to address. And for me, I have to adjust basically the pitch lengths that go from the swash plate to the blade grips, because I'm getting a little bit of positive pitch right there. So I'm going to fix this mechanically. Now, if you're lazy and you don't want to fix it mechanically, then you can just go in here and use your arrows on your computer and start making changes until your blade grips are at 0 pitch. With Tron helicopters, SAB helicopters, many other helicopters, you have these lines on the blade grips and they get you really, really close to 0. When you get those lines perfectly aligned with each other, you can, another trick that is actually really useful to find the exact 0 pitch is to fold the blades together, like I'm going to show you right now. So basically you take your blades, you fold them like that, and even though the lines here are showing me that I'm at 0 pitch, I'm not. So I am at this point going to cheat, and I'm going to start changing the settings on rotor flight to make those 2 blades be at exact 0 degrees. Here we go. So look, I'm all the way up to 8.5. And there's really nothing wrong with having this number a little off. I feel like that's as close to 0 pitch as I'm going to get. That's pretty close right there. The next step is to set up your main rotor geometry, and that includes your cyclic and your collective calibration. First thing you do is you put the blades back on your helicopter, you plug in your flight pack, and you plug it into rotor flight. You leave your transmitter off. You do not need your transmitter for this step. And then you fire up rotor flight, and you're going to go to the mixer screen once again, which is right here. And where we were at before, we already dealt with all the main rotor settings. Now we're going to be dealing with the main rotor geometry. So the first thing we're going to do is we're going to calibrate the cyclic. And in order to do that, you need to get a pitch gauge. In this case, I have an iPhone, and it's hooked up to the blade with the X-Guard phone mount. It's a really cool gadget. I recommend you look at it, but if not, any pitch gauge will do the trick. So what matters is that the blades are parallel to the boom, facing front and back. As you can see here, my collective trim percentage has changed. I made some mechanical changes and got it a little better. So again, what matters is that your collective is at 0 degrees at this stage, right? And then you're going to go ahead and turn on the mixer overwrite. And I think this value right here is what you're going to be looking to change. But as you can see here, I think default is 25. It depends on the version that you have. But anything between 60 and 100 is what you're looking for to get the right amount of pitch. So you're going to deal with the roll axis right here. So you're going to start increasing this, and don't hold this and let it go, because you're going to be making a drastic change and it's going to jerk your blades and your pitch, and you might lose the calibration on your pitch gauge. So what you do is you hold the arrows on your computer and start increasing this number. And as you can see, if I change the screen right here, we're only at like 3-some degrees. So we need to just bump this number, that number there, that cyclic calibration percentage right here. We need to increase that number until we reach 9 degrees. Now, if you don't want to wait forever, you can increase it in increments of 5 or 10. Again, if you get too aggressive, you're gonna jerk everything, and then you're gonna you might lose the calibration on your pitch gauge. So I'm gonna keep increasing until I see something close to 9 degrees. And there's no pitch gauge in the world, I don't care what anybody says, that is extremely accurate. So we're trying to get really close, but we don't have to be perfectly exact. So as close to 9 as we can be, that's 9 degrees. And I'm at 83.3 right there. So now what I'm going to do is I'm going to take this slider here and use the left arrow so I don't, again, jerk things too drastically, and go all the way down to -9 degrees. Let's see what happens. Let's see if it gets us there. And as you can see, we're at 8.73 on this side, and we were right at 9 on the other side. So that is pretty close. If they're not exactly the same, it could be for one of two reasons. Either your pitch gauge is not calibrated correctly, or it's off, and a lot of them are. Or it could be that you're not at true 0 when you're right here. I think I am pretty close. I don't care about 0.2 difference. I think it's more than sufficient. So we're going to go ahead and move forward now and work with the collective calibration right here. So for the collective calibration, we're going to go down here to the collective, okay? And again, obviously enable mixer override needs to be turned on right here. So we're just basically going down here to the collective, and we're going to start doing the same thing we did before. We're going to start increasing that value, and we're going to look at the pitch gauge. And I had to reposition my phone, and that's one of the things that I just don't like. Pitch gauges, they never really work very accurately. So I'm going to go to 9 right here, and then we're basically doing the same thing we were doing before. We're just, you know, I'm only reading 2.2, so I'm going to have to start increasing this, and I'm going to increase that slowly in increments of, I don't know, 10. Okay, so we're getting close at 85, 90, 95, 9 degrees. So now what we're going to do is we're going to move this down to -9, right? And we're going to check to see if they're equal. They're really, really close. I don't think I want to mess with it. But if they're off, what you want to do is you want to mess with this number right here, which is the collective geometry correction. So because I have less on the negative side, I need to shift everything to the negative side, right? So I'm going to lower this a little bit and see what happens. I'm up to 8 let's see here. Yeah, that's way better. I think I'm at 8.9 almost. We'll see what happens when I move this back to the positive side right here. You can see how the whole system shakes like crazy. That's the worst thing you can do to a pitch gauge, regardless of what type of pitch gauge it is. And look at that. We're almost exactly the same. 8.79. And again, it doesn't need to be perfect. It needs to be close. and 8.9. Okay, so it's really close. And you know what, if I move this thing back down to another number, I bet you things are not gonna ever be perfect anyway. Now I'm 8.94. Again, these pitch gauges, I don't care if you use a phone or a dedicated pitch gauge, they never really work well. And this is 8.88. I mean, that's as close as it can be. If you want to be like as close as you can possibly be, then increase that 100 number here, that collective calibration, to get the true 9, right? Although I'm being really picky here because, again, this doesn't need to be exact. Now, if I keep going, let's see what happens at 12. Yeah, 11.86. So that's really close. So I'm very happy with the setup on my collective right now. So the next thing I'm going to do is I'm going to mess with these numbers right here. So cyclic blade pitch limit, okay? For most helicopters, and this pertains, this is applicable for helicopters that are perhaps between the 600 and 700 size. I would say no more than 14 degrees to be safe. You could go a little higher, but it's risky. Now, collective blade pitch limit, I like to do 14 as well. And then for the total blade pitch limit, well, I know that the Tron can handle probably 24, but if you want to be conservative, I would do something like 22 right here. Okay, we're going to start working now on the tail rotor settings. Quite simple task. Some people get confused for the simple reason that it's very difficult to figure out what the angle limit is for clockwise, counterclockwise, but we're going to get to that. As you can see, my tail is being shown here on my helicopter. Blades are folded. And the reason I folded the blades is because it makes it a lot easier. Let's move the angle a little bit so they can be seen a little better. Just like that. And then we're going to go to the same screen right here, the mixer, and we're going to enable the override. So the first thing I want to see is that when I move the yaw, that my tail is moving. And as you can see here, it is moving. So that's good. So I'm going to make sure that I am back at 0 right here on the yaw. And then we're going to move up here and start over. So variable pitch, that's what we need. We don't have a motorized tail or a bidirectional tail. We have a variable pitch tail. And then the yaw control direction I know is okay. I reversed the servo, so it should all be fine. If not, you can go here and reverse it. And then as you go into the yaw center trim, so you see how I folded the blades on purpose because it's easier to find at 0 pitch. So what we're going to do is we're going to start moving this value right here up and down until we get the blades to be perfectly together, right? So as you can see, as I move that value, the blades start to get, let's see here, that's it. So right about there. This doesn't need to be perfect, but close enough. And as you can see here, I ended up with 2.7 to get those blades perfectly centered. Then the next thing we're going to do is we're going to set first the clockwise and counterclockwise blade angle limit. I have a Tron, so I know it's close to about 44 degrees for clockwise, and it's about somewhere in the 34 degree for counterclockwise. One thing that some people do is they measure the blade angle. But in order to measure the angle, this is quite tricky because let me show you with the tail blades. So basically, as you start moving, if you're able to measure the angle between the two blades, this angle right here, basically half of that angle will be your pitch deflection. It's not really that easy to it's not that easy to figure out. So it's best to get a hold of somebody that has set up rotor flight on the helicopter you have, or you can start with somewhat of a conservative number like I showed you here. You can have somewhere in the neighborhood of, I would say, 40 to 45 degrees for clockwise and 30 to 40 degrees for counterclockwise. And once you've done that, and you go in here to the yaw, and then you go pretty much say to the relative same number that you picked about right there. And then you're going to start increasing your yaw calibration until you're about to bind. So let me pan over to that camera, straighten the blades, and as you can see, the pitch slider is still a ways away from the limit. We're gonna start increasing this yaw calibration number, right, until the pitch slider starts to bind or starts to get close to the end. And let's see. Normally that number on most of my helicopters ends up being somewhere between 50 to 60. But we'll see what happens here. And I ended up at about 54. Now what happens if I move this to the other side? Let's see. I think I'm good. I think I'm perfectly fine. And if you see that you're binding, if you're binding on one end versus the other, then what you do at that point is you basically reduce the number here on the angle limit. Again, some people measure the true blade angle. It's very hard to do because you have to, again, measure the angle between the two blades and cut that in half. Some people use a piece of paper and they basically create an angle with paper, and then they kind of get an idea. If you take the corner of a piece of paper, that's 45 degrees. If you fold it all together and you make it kind of pointy, then you got 60 degrees. So if you have a 60-degree angle between the two blades when they're folded, it means you have 30 degrees of deflection. So it gets you close. But based on experience, this is not as picky as some people think. If you start with like something like 45 and 35, it's going to get you really close, and the tail performance is going to be really, really good. So I would start off with that. And again, if you know somebody that has a helicopter, I know with the Tron, 44 and 32 to 34 works really, really well. And then your yaw calibration is going to be right in the low 50s or so. So anyhow, that wraps it up for the entire mixer section. And up next, we're going to talk about the following section, which is the gyro section. Okay, let's talk about the gyro screen right here on RotorFlight. So basically, the gyro screen addresses filters. And to explain filters a little better, all flabberless units out there on the market, whether it is the Mikado V-Bar, the Icon, the Brain, the new Spirit Wave, all of those flabberless units have built-in filtering. Filtering is super important because helicopters have inherent vibrations, and you want the gyro to ignore those vibrations and not consider the vibrations a movement of the machine so that they don't overcorrect or undercorrect during certain circumstances or certain flight conditions. What's important about this that we need to address is the fact that the more filtering you do, the slower the response will be, because as the processor is trying to filter out these harmonics and these vibrations, it's going to slow down the response from the movement of the helicopter to the time when the actual processor makes a correction within the control loop. So we want to keep the filters as low as we possibly can. This belongs to a more advanced video where we're going to talk about filtering and how most of the guys that are in the developing RotorFlight developer community are running their filters. But for the first time, when you first set up RotorFlight, I recommend you go with more of a default situation just to be safe. And again, this is not going to slow down your response to where it's not going to be comfortable to fly, but it's just a safe setup. So as you get to the gyro screen, I don't think any of these options are turned on, but for sure the gyro low pass is super important because the low pass cuts all the vibrations above a certain frequency. So 100 hertz is really good. There's no reason to go any lower. The higher the number here, the less filtering you're going to have. I'm running 150 right now, but I recommend you start with 100. So we're going to leave that at 100 right there. You don't have to worry about any of the stuff right here, but you do need to get into the gyrodynamic notch filter settings and enable that. And basically what a notch filter does is it targets a very specific frequency and it only filters that frequency. It doesn't filter anything else. So you want that enabled right there. And then as we get down here to the RPM, this is important because RPM notch filtering targets a frequency that is specific to the RPMs in question here. And Rotorflight already knows what RPM you're running because we taught it when we were back in the motor section, what your gear ratio was, what your tail gear ratio was, what your motor is, and it knows based on telemetry what your RPM is. So normally I like to set this between somewhere in the 800 range to, I don't know, 3000 or something, just to make it really broad. And then as we get down into the gyro RPM notch filter banks, so the main rotor we should enable, and we can leave alone the value at 2.5. And basically this fundamental frequency notch type basically works as one per revolution per se. So any imbalance on the main rotor will be filtered by this right here if you have a blade out of balance or if there's something going on with your main rotor. Then the second harmonics should also be enabled, and this actually filters blade flapping, which blade flapping is basically the up and down movement of the rotor blade that is, of course, more pronounced as the blade gains or loses lift. And this could be because you made a change in pitch, or this could be because of the actual dynamics of flight and the gyro is making corrections, right? So that does it for that. We don't need anything else. And then for the tail rotor, we should enable the fundamental frequency, which is similar to the fundamental on the main rotor, and we should enable the second harmonic. Now, the third and fourth harmonics on the main rotor wouldn't hurt to turn on as well, because these address lingering, longer lasting vibrations, very high frequency harmonics in the main rotor. So we should enable those as well. Other than that, I think this would do it for the gyro, and if you have this right here, you should be good to go. Now, if you're setting this up on a little helicopter and you're going to fly to 5,000 RPM, then obviously bump the tail rotor maximum filter RPM to like something crazy higher, right? Because your tail rotor is going to be super high, and your main rotor is going to be way higher, so you might want to bump the 800 to like, I don't know, 2,000, and the 3,000 for the tail to be something insane like 5,000 or 6,000. So use your discretion on these. Normally, as a rule of thumb, I set these to be about half of what I normally would fly the helicopter at. So after we're done with that, save and reboot. And now we're going to move forward to the rates section. So now we're finally in the rates section. So as you look at Rotorflight and you go to rates, you have rate profile 1, 2, 3, all the way up to 6. As I showed you on my previous video where we were explaining how to set up your first model on the TX16S, you have switch SB controlling your rates, where switch SB is all the way down, you're in rate profile 1, and if it's in the middle, it's profile 2. If it's all the way up, it's rate profile 3. So rate profile 3 is what I fly the most often, and this is what I usually set up. Now, there's different options here. A lot of people like Raceflight. It's a pretty simple, I think it's Betaflight. It's a pretty simple rate, or Betaflight or Raceflight. It doesn't really matter. They're very similar. But it's a pretty simple rate system. So basically, this is degrees per second, right? So if you want to peg your roll stick, which is your aileron stick, say for example all the way to the right for intents and purposes, you're going to do 180. If you want the helicopter to go from upright to inverted in 1 second, right? So that's 180 degrees. So I think that's a conservative number for the cyclic for both roll and pitch. And then for the yaw, if you want a full pirouette per second, then you would obviously do 360. I don't use Raceflight or Betaflight. I use actual, and we're going to get to that in a second. But anyhow, this is your expo right here. So you can set up your expo to be 30% or whatever, say 40% for elevator and 30% for aileron or whatever you want. And then obviously you save. Once you've made the changes and you've saved this, then you can copy that profile 3 to profile 2 and profile 1 so that all your rates are the same. and have a baseline and then start modifying different rates from that point on. I use personally the actual rates, and the way that the actual rates work is actual has a center sensitivity and a max rate, okay? So the max rate only comes into play when you have full stick deflection for a sustained period of time. I personally run 290 degrees for my roll, 290 degrees for my pitch, so my aileron and elevator, and I run 580 degrees for my tail. And then what I do is my expo here, I set it at 0.2, and I set it here as well at 0.2, and I set it at 0.2 for the tail. Now what I do with that is my center sensitivity, I do 250 for my roll, and I do 250 for my pitch. So aileron, elevator, 250 degrees per second, center sensitivity, and my yaw, my tail, is 450 degrees center sensitivity. So basically the feel that you get, that instant response you get when you jab the stick, is going to be basically your center sensitivity right here. And you can play with these numbers, like as you can see here, see the graph. If I increase this expo to 0.5, you can see how it steepens that. It makes it less responsive around center, right? But you're going to have to play with this for a while and see what's your preferred method. I recommend you start with center sensitivity and max rate being the same, and then increase your max rate as you feel comfortable, and then maybe play with the expo to get it to where you want it to be. And then on my collective, I like to run about 13. So remember, we told the system how much collective to run, maximum collective to run, but we didn't tell the system what amount of collective to give us during flight. We just told it what's the maximum that it can go to. So this is where you tell it how much collective you want to run. I want to run 13 degrees, positive and negative, and I want that rate to be the same for center and the same for max, and I don't want any expo. I just want 0 expo on my collective. So anyway, after I'm done with this, I click save, and then I like to copy this to profile 2, and then I like to copy this to profile 1. So now all my 3 profiles, as I move my SB switch, will be the same. And then eventually, as I start flying, I will make changes to rate profile 1 or 2. For example, I'll do profile 1 with a much lower setting here. So if somebody wants to fly my helicopter, it won't have 13 degrees of collective. It might have only 11, and it won't have 450 degrees of, or 580 degrees of pirouette rate, per second. It'll have probably 360, which is one pirouette per second instead of almost 2, and so forth and so on. So I hope this helps with the rate screen. Up next, we're going to go to profiles. There are a million options here, and to be totally honest with you, you don't really have to touch anything the very first time you set out to fly rotor flight. Your PIDs are pretty acceptable for 90% of the people. Again, I'm going to do a future video where we talk in depth about fine-tuning, including filters, how we lower our filters, how we fine-tune the helicopter, including making changes to the P, I, and D values. But pretty much what you see here is pretty acceptable for most people. But some things that I would actually change right here is I would probably increase the proportional gain on the pitch axis to like 70 or 80. And again, these are very conservative numbers. I would increase the yaw or the tail gain up to 90. And again, to be redundant, these are conservative. I'm running over 100 on pitch, and I'm running 120 on tail, but this is a good starting point right here. I would leave the integrals alone for roll and pitch, but I would increase the yaw to at least 150. And then the D gains, I would leave alone the roll, which is aileron, and I would probably leave alone also the pitch, which is the elevator. And then I would drop the yaw, the tail, a little bit down. And then feed forward is what actually allows you to have a crisper stop. So if you're overshooting when you do a continuous flip or a continuous roll, say you're doing a continuous flip and then you stop the helicopter horizontal and you feel like it's overshooting, then you would increase If it's obviously a flip, it would be pitch, which is elevator. You would increase this number to 110, 120. I think on some of my Trons I'm running 130 to make them stop in a crisp fashion. And then the boost is basically similar to what V-Bar calls the paddle sim. It's really nothing to do with paddles or fly bar. It has to do with the response time you get right off the bat when you first jab the stick. Everything else in here can stay the same. You don't have to really do anything, at least to get started. And we're going to do a more advanced video later on explaining PIDs and fine tuning. But the one thing that I need to do here is I'm in profile 1. And if you recall, profile 1 is triggered by my transmitter using SE switch, right? So when SE switch is all the way away from me, I'm in profile 1. When it's in the middle, I'm in profile 2. When it's towards me, I'm in profile 3. So I'm going to go ahead and save this because I'm using, as you can recall here in the motor screen, because I'm using pass-through. In other words, I'm using the Hobbywing governor, right? I need to set the throttle value here, and this is what the Hobbywing will see as the throttle to accelerate to. So for bank 1, which is my profile 1, basically bank 1 in V-bar terms, I'm going to go to 60, and I'm going to save this. Then I'm going to copy this to profile 2, and I'm going to copy it also to profile 3. And then when I go to profile 2, I want this to be at 70 for my throttle. And then when I go to profile 3, which is my all-out 3D mode, I want this to be 80, which is going to be crazy RPMs. But obviously, I'll fine-tune this later once I get my first flight on the helicopter. But this will get me going for now, and I think that does it. So I already created the mode for arming. When it comes to adjustments, I haven't done that here. I already showed you how to do that when I taught you how to create your model on the transmitter, but I'm going to go ahead and revisit this real quick and get the adjustments done for the banks and the rates. I have my TX16S right here, and I am going to put a picture-in-picture with RotorFlight, and we're going to the adjustment section. So before we actually do any of that, let me, I was playing with this a little bit. So just to double check, so as you can recall, the SB switch here is adjusting our rates, and that's aux3. And this switch right here, which is the SE, is adjusting our banks, which is aux2. So aux2, aux3. I'm going to do it again, although you should have this already configured if you watch my previous video. But we're going to go to adjustments right here, and we're going to change this to mapped. And we're going to do aux2 and aux2, and we're going to broaden this range right here all the way, maximum and minimum. Same with this. And then when it gets to here, we're going to do profile selection. And as of right now, we have 3 profiles. So as you can see, profile 1, profile 2, profile 3. And we're going to save, and we're going to double check that that's working correctly. So we're going to profiles now, and we're looking at this profile 1 changing to 2 and 3. That's 1, that's 2, that's 3. So that is working correctly. Now let's go back to adjustments. And now what we're going to do here is going to turn this on to mapped 2. And we're going to go to aux3 and aux3, just like we did before with aux2. We're doing it with aux3, broadening this range all the way to beginning to end. And then here we're going to select rate profile selection. We have 3 rates, so I'm going to set this to 1, 2, 3. And then as you can see here, it's going to change. That's on rate 3, rate 2, rate 1. As you can see right here, I'm going to save this. And to verify, I'm going to go to rates. And again, as you can see here, you can see we're on rate 1, rate 2, and rate 3. Okay, I know this video is getting super long, but I want to show you how to create a 4th profile, because a lot of people have asked me about auto rotation bailout, and that is the easiest way, especially if you're using the governor that's built into the Hobbywing or the Scorpion or the YGE. So what we're going to do here is we're going to show you this picture-in-picture. And as you can see right here, obviously we already talked about this. We have profile 1, profile 2, profile 3. And as you can see up here, the actual center pulse width in microseconds is moving from here to here to here. In order to have a fourth profile, we're going to have to make some changes to the transmitter, right? Very easy to do it. So you can see now I'm going to 1, 3, and 4. Well, we don't want that. So what we want to do here is we want to go to the model menu, and we want to go to our mixes and go to our profile mix, which we created, which is channel 7, edit. And we want to go into this offset right here. And we're going to start playing with this offset until we see that this goes to 1, 2, 3. And as you can see now is 1, 2, 3. All I did is I moved that offset to -40 right here under my mix for profile, channel 7, right? Okay, so now I go to the special function screen. I do the plus. I do special function number 1. The trigger is going to be the switch right here, the SG switch in the middle position. And with that trigger is SG dash. I'm going to overwrite, and I'm going to overwrite channel 7, and I'm going to do the value at 100. And I'm going to enable it. So what that does is when this switch is in this position, it takes that servo output. If you look at that channel 7, which is profile, you can see the output with that switch there is going to plus 100. So now on the screen, you can see that I am at profile 4. If I let go of this switch, I go back to whatever profile I am on this switch. So all the way away from me is 1, in the middle is 2, towards me is 3, and then this one in the middle will take me to profile 4. If I am all the way out away from me here, I am in run mode. I'm following the profile defined by this switch. If I'm all the way towards me, I'm also on the profile that is defined by this switch, 3, 2, 1. But again, if I'm in the middle here, I go to profile 4. So then what you do is we save this right here, and then what you do is you go to profiles, and you take your profile 3 and you copy that profile to profile 4, just so that we carry all our settings, our PIDs and so forth. And then we go to profile 4 and we change under governor settings the maximum throttle to something like 28%. And what that allows Hobbywing or most DSCs to do, so if I'm flying and I want to do an auto and I just go to the middle position here, and it takes me to this profile 4, as you can see here. Now my ESC is at 28%, so it cuts the motor, but when I let go and go back to run, it's going to spool up very quickly within a second. And the number that we used right here under the motor section for the auto rotation timeout, 30 seconds. That's how long you have before you have to bail out of it. If you don't within 30 seconds, then you'll default back into slow spool up mode again. Now, it's important to keep in mind that if you're doing an auto rotation and you basically hit just one click and you'll land, you better make sure that you click all the way towards you before you spool back up, because if not, it's going to be so violent that you might break your helicopter. So but that's how I do the auto rotation bailout, and I hope that was helpful. Okay, let's wrap this whole thing up. All right, so before you go flying, plug in a RotorFlight into your Nexus and just double check the movement on your helicopter. So move it forward, make sure the helicopter on RotorFlight moves forward, then let it sit again, then move it side to side, like make sure the aileron direction is correct, and then move the yaw like a little bit, like left to right on the tail. Yep, so, and it should move correctly there. Last but not least, turn on your radio and plug in your flight pack, and then make sure that all the control surfaces are moving correctly, positive and negative, right and left, back and forth, tail to the right, tail to the left. Make sure all the corrections are correct and all the control surfaces are moving correctly. And then don't forget to do a quick test. Arm the unit by pushing the SA switch all the way forward, and then release the throttle hold by moving your SG switch all the way forward, and it should spool up. And there it goes. Now, once it settles into an RPM, you can test the auto rotation bell out. Move the SG switch to the middle position. There we go. Middle position. And then release it within 30 seconds, and it should spool up super fast. There it goes. Takes like a second or two. Now move it all the way towards you, the SG switch, and now you're in full throttle hold. So now if you go all the way forward with SG to the run position, then it's a slow spool up again. So everything seems to be working perfectly. So anyhow, I appreciate your patience. I appreciate your time. This was a very long video. It took me over 3 days to do it. Best way for you to support me and my YouTube channel is to click the subscribe button. Also, check out bkhobbies.com, of course. I want to thank my wife, Susie Kammerer, for helping me. This has been like a lot of recording and a lot of re-recording and a lot of tuning to get this video done. So I hope this video is very helpful to you guys. I wish I would have had a video like this when I started with Rotorflight. Anyhow, we'll be in touch. I'm going to do videos about telemetry. That's a completely different topic on its own. The LUAs and the scripts that you can install on your transmitter. So I hope you enjoy, and I'll see you next time.